tanah air beta pusaka abadi nan jaya Indonesia sejak dulu kala selalu dipuja-puja bangsa. Di sana tempat lahir beta, dibuai dibesarkan bunda, tempat berlindung di hari tua sampai akhir menutup mata. Sejak dulu kala selalu dipuja-puja bangsa. Di sana tempat lahir beta, dibuai dibesarkan bunda, tempat sampai akhir menutup mata.
Iya. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak dan Ibu. Selamat pagi Bapak dan Ibu. Terima kasih. Salam sejahtera dan sehat selalu untuk kita semua. Selamat datang pada hari ini Kamis 25 Agustus 2022 dalam acara Shortcourse HAKI 2022. Mohon tepuk tangannya semua. Kita semangat, kita optimis pada hari ini. Saya merasa sangat bersyukur dapat berada di sini di tengah-tengah Bapak dan Ibu di ruang Flores Hotel Borobudur Jakarta. Dan izinkan saya Dini Herfiani untuk membantu acara pada hari ini. Kita akan langsung ke acara inti. Pada hari ini ada narasumber, Mr. Andrew Taylor. Good morning, Mr. Andrew. Mr. Andrew Taylor. Good morning, we are so glad to have you here. Dengan moderator Ibu Prasanti Widya Sarli. Untuk itu kepada Ibu Prasanti kami persilahkan untuk naik ke atas panggung. Terima kasih.
Hello, good morning, everyone. Allow me to speak in English as our speaker today is going to speak in English, I assume. First of all, good morning and welcome to the third day and the last day of our HAKI conference. And I'm sure that everyone is both tired and also very excited to have our upcoming guest, Mr. Andrew Taylor. So perhaps firstly, for the benefit of our speaker, let me introduce a little bit about the HAKI conference. So actually HAKI is an association in Indonesia, and our conferences are one of the most awaited and sought after conferences for our community. And we have this conference annually every year. However, during COVID, we were not able to hold it. So actually, 2022, this year is so special because finally we can come together again. So now, let me introduce you to give a brief introduction about our speaker today. Dr. Andrew Taylor is the technical director of KPFF Consulting Engineers in Seattle, where he is the lead design for special seismic systems, such as seismic isolation and seismic damping. He is also a specialist in seismic design of reinforced concrete structures. We like that, and has an experience of over 30 years in structural engineering. Not only that, Dr. Taylor has numerous technical committee experiences, both at the local and national level. What we know, of course, is that currently he is the chair of the American Concrete Institute 318 Building Code Committee, which will complete the next edition of the U.S. National Concrete Building Code in 2025. And other than that, he is also a member of the 2022 edition of the ASCE 7 Building Code. He has so many experiences. He has been part of the Applied Technology Council project, ATC 98, on the use of high-strength reinforcement for seismic design. And he was also the chair of the Earthquake Engineering Committee of the Structural Engineers Association of Washington. Dr. Taylor, affiliate professor in the Department of Engineering at the University of Washington, where he has enjoyed teaching courses in structural analysis and reinforced concrete design. So it is such a pleasure for all of us to welcome you here today with us, virtually, of course. Big applause to Andrew Taylor first.
Thank you.
So, Andrew, I hope you don't mind that I don't know where I should look at right now so that you can see me on the screen, but
I can see you.
Near there. So let me give a brief introduction before we go to your presentation about what you are actually going to present today. So Andrew Taylor, because of his credentials, is the perfect person for us to actually learn about ACI 31819. Today, in this short course, he is going to give an overview of changes in the ACI 31819 building code. But not just that, he also will give us like a looking ahead type of perspective of ACI 31825. So as we know, the first edition of the American Concrete Institute Building Code was actually published in 1910. However, it has consistently been reviewed and revised over the years, and especially between 2008 and 2014, they made a major or a reorganization of the building code so that it will be easier to be used, which is now called the ACI 31819 and ACI 31819R. I'm sure everybody is very well knows about this. So today he will give us an introduction about what are the big major changes of the ACI 31814, and then how it looks like right now in ACI 31819. And I heard here in the abstract I read that you will also give us a little bit of the process development of what will be the next edition of ACI 31825. Kalau bahasa Indonesia kita dikasih kisi-kisi 31825 nanti seperti apa ya. Okay, so without further addition, I will give the screen to you, Dr. Andrew Taylor. Please.
Thank you.
Start. Yes.
Let's see. I will share my screen, which, there we go. Do you see my presentation?
Hello? Yes.
Yeah,
we can
you
see
do.
your presentation.
Okay, wonderful. And question is, can you hear me all right?
Yes.
I just want to make sure you can see and hear me. So, okay, very good.
We can see and hear you.
Very good. Thank you for inviting me today. It's always a pleasure to be involved with this conference. I have attended this conference 2 times in the past before COVID, and I've very much enjoyed my time in Jakarta and also meeting new people. I see many familiar faces in the audience today. Perhaps someday in the near future, I will be able to return and speak in person. But again, thank you for inviting me. I will be speaking in English, and I wish I could speak in another language, but I express myself best in English. So I appreciate your listening to my presentation in English. I want to point out that the shirt I'm wearing was a gift from the conference organizers the last time I was in Jakarta. So I thought that in honor of that experience, I would wear this shirt today for my presentation. So thank you very much for that. All right, well, I think we'll get started. Here's the title slide, which simply tells you that I'm going to present ACI 31819 and how it has changed between 31814 and 31819. And then since I'm chair of the current 318 committee, I will give you a little preview of what we think will be coming in 31825. So I hope you find that interesting. So let me make one adjustment to my screen here for a moment. I'm going to move. Okay, I'll stay there. And I'm going to move my camera down so I can speak directly. Pardon me for this technical change. Give me a moment here. That way I can look more directly towards you. There we go. All right. Now I will also change this way. Okay. So I assume that you can see me now, and I can look at you more directly. Okay. So thank you very much for inviting me. As I said, I will be speaking, let me back up. I will be speaking for a little over an hour, maybe 90 minutes, and then we'll have time for questions. So I will attempt to answer as many questions as I can. The two main topics that I will talk about are the changes, as I mentioned, between ACI 2014 and ACI 2019. And then I'll be describing some of the changes, not all of them, because we're still working on it, for the 2025 building code. I want to point out that in this presentation, there are a number of changes to ACI 318.14 to 19. But in this presentation, I will only cover the most important ones, the major ones, and I will let you know what these most important changes are. But normally, when I present about the changes between ACI 318 and 14, it is about a 6-hour presentation. So I've condensed that, and I'm going to cover the most important points today. I want to point out that since 2014, the ACI code has been organized into 10 sections, and you see them listed here. The first is general, which contains information on how the code is to be used and interpreted, and so on. And then loads and analysis, member strengths, joints and connections, seismic materials appears in a section, material and ductility, strength and serviceability, reinforcement, details, construction-related provisions, and evaluation of existing structures. This is just to give you a very large overview of how the code is organized. Now, I want to point out also that there are several editions of the code available, including one in SI units, which is the one that I'm assuming that you would be using. The one on the right is the inch-pound units version, the one that I use most. You can see the difference here is shown in the upper right corner, inch pounds versus SI. There are also editions of the code in Spanish, Chinese, and I believe one or two other languages. But most importantly, the slides that I'm showing you today are mainly listed in the American units or inch-pound units. However, I've attempted to translate those units in key points within this presentation into SI units. For instance, I've converted kilopounds per square inch, or KSI, into megapascals. I've converted forces into newtons, and so on. So hopefully you'll be able to follow along in familiar units. And I've listed also here, just for your convenience, the conversion factors if you wish to convert anything from the inch-pound version to the SI version. One factor I find very interesting is the very last one, pounds per square inch times 0.006895 is megapascals. And I wanted to note that that is the famous number associated with the secret agent James Bond, 0.007. So remember that number if you're ever converting from pounds per square inch to megapascals. All right, let's get started on the actual contents of the code. When it comes to repairing existing buildings, those that have been damaged or deteriorated, the code refers to the document ACI 562, which is a repair and rehabilitation code. It's a very comprehensive and helpful code. So if you are encountering a situation where you need to repair an existing structure, please refer to that code. But we also say in ACI 318 that the provisions for new construction or new design can be used when repairing an existing structure. So if you're using ACI 562, you will also refer back to ACI 318, which is what we're talking about today. So I'll skip way to the end of the code. The very last chapter is chapter 27, and its topic is the strength evaluation of existing structures. This applies when a structure is completed and but hasn't been occupied yet. However, there may be some question about the strength of the structure, and this often happens if, for instance, a concrete test, strength test comes in that's too low. And so it may be necessary in some cases to evaluate the strength of an existing structure in order to certify it for occupancy. Now, what is generally well understood by engineers is to look at the structure that's in question, if perhaps the concrete strength is lower than expected, and perform calculations to evaluate that structure. I think many of us understand how to do that and to see if the lower strength is perhaps acceptable. But what is not well understood generally is the procedure for actually performing a load test on the structure in the field. And this load can be applied in a number of different ways with heavy blocks, with tanks of water, with hydraulic jacks, a number of ways. But there are two test procedures described in chapter 27. If you are encountering a situation where you need to actually test the strength of a structure, one procedure is called the monotonic test. It takes a long time because, as you can see in the lower graph, that you have to apply the load and hold it for 24 hours, so a full day, remove the load, and then evaluate the deflection after another 24 hours. So it takes at least 2 days to perform this test. There's an alternative procedure, which is called the cyclic procedure. That is presented in the document ACI 437. And as you can see, the total time for one test is 120 minutes or 2 hours, meaning that this test can be performed much more quickly, and perhaps several tests can be performed at different locations in a structure if necessary. It's a cyclic load test where the load is increased and then decreased, increased again, and so on. So I just want to make you aware of those testing procedures that are available in 318 and in ACI 437. All right, now we're going to go back to some of the more fundamental aspects of design that are covered in ACI 318. I want to point out something which is actually not new in the code, but it's very important, so I want to bring it up. In previous years, previous editions of the ACI code, let's say ACI 31808 2008, the loads in that code were based on a US document called ASCE 705. In that code, the wind loads that are specified in ASCE 705 are not factored, meaning when one is creating the load combinations for design, you have to multiply the wind load from ASCE 7 by 1.6. So it's a factored load in that case. Now, what has happened since then, and again, this is not new, but in the last 3 editions of the ASCE 7 load document, that document has changed from service level loads to strength level loads. And the load factor used in load combinations is 1.0. So the wind loads as presented in ASCE 7 now are already factored. So it's a very important distinction to be made aware of for wind loading, because the difference is a factor of 60% for wind loads. So if you follow current practice and use factored loads in your design, whether they're from ASCE 7 or some other document, as long as they are considered strength level wind loads, then the load combinations in ACI 318 are correct. Okay, just a very important point about wind loading. Another aspect of concrete design that I'm involved with quite a lot is the vibration of floors, either for sensitive occupancies like medical MRI machines or electron microscopes, or for human comfort, such as in apartment buildings, offices, and so on, where occasionally floor vibrations can be a problem. Now, generally, concrete floors perform quite well from a vibration standpoint, and typically we don't have issues with them. However, there are cases, for instance, long spans, very high precision machinery, or where there's a rhythmic loading, such as an exercise studio or vibrating machinery, and sometimes precast concrete elements can exhibit vibration that is not acceptable in a particular situation. So in the commentary to ACI 318, there are references for procedures and methods that can be used to evaluate floor vibrations. And I want to point that out because occasionally that is something that just about every consulting engineer needs to deal with. All right, now we're going to talk about types of members, meaning slabs, beams, walls, and so on. The first type of member we're going to talk about is one-way slabs. So these are slabs that flex in one direction rather than in two directions. And of course, they're the simplest type of slab. With this type of slab, the one-way bending slab, we are concerned with all structural systems, but in particular this one, about the potential for collapse under extreme loads that are actually we don't even consider in our design. What we would like to do is to preserve the integrity, the structural integrity of these elements, these slabs in particular, so that they will remain in place. They may be severely damaged, but they will have a good chance of not collapsing. Because as we know, collapse causes of one element in a structure causes loads on adjacent elements. So we want to preserve this structure in its original configuration, even though it may be severely damaged. So there are new provisions in the ACI 318 code to provide very minimal, inexpensive, continuous reinforcement in the in one-way slabs to provide a high degree of confidence that they will remain in place if they're subjected to some very extreme loading that it wasn't anticipated in the original design loads. So that's what's new about one-way slabs. Not much has changed, except that there's those new provisions for integrity reinforcement. So regarding two-way slabs, you may be interested to see that two of the methods that have been in the code for a very long time, maybe, I don't know, 50 to 80 years they've been in the code. The direct design method and the equivalent frame method from 318.14 have been removed. Now, this is not because there's anything wrong with those methods. Those methods are completely valid. It's just that they are not used very often. Most of the time they're used primarily for preliminary sizing, but not for final design. And we looked at those, and we are trying to save paper when we print the code. And so what we did was we took those methods out, but we left references in the code that said, for instance, 821, the direct design method or the equivalent frame method, which have been removed, are valid. You just have to refer back to ACI 318.14 for the rules about how to use them. They aren't eliminated. They are just not printed in the current edition of the code, because we found that in practice they actually weren't being used very often, but there's nothing wrong with those. That same provision appears in section 6241. So those methods are still available. Here's a very important one, especially if you're doing commercial design of multi-story buildings. We all know that the mechanical engineers want to put holes at the worst possible locations in the structures that we design. That is right next to columns. They want to put holes through the slabs where the pipes come and conduits come down the columns. And so there are rules in ACI 318 about how to evaluate the punching shear strength of a slab intersecting a column. So a very common form of construction is flat slabs without any drop panels or shear caps, just a flat slab intersecting a column. And in order to evaluate punching shear strength, we need to account for those openings. And you see in the illustrations on the right, it describes how this is done for various situations, shapes of holes, and so on, how to evaluate that green dashed line, which is the perimeter of the punching shear zone. A big change is that it was determined that previously in 318.14 that the distance from the column that a opening may be located without affecting the strength of the column, punching shear strength, was 10 times H, where H is the thickness of the slab. And that created more situations where it was harder to design for openings like those shown on the right. That has been revised to 4H, so it's much smaller. That is, openings can be within or no closer than 4H from the column, but they and then they won't count against the punching shear strength. So this is a significant change, and I think makes life easier for engineers designing flat plate structures. Another change is that it was determined that for very thick slabs, so this figure shows actually an actual concrete slab in a building in the United States that was 2 feet thick, which is about 300 millimeters, I think. So it's quite thick. It had many stories of structure built above it, but this was the base of these upper floors. And it was noticed, there was a near failure because the punching shear crack, as shown here, formed and moved out and did not intersect the top reinforcement that was there for preventing, partially the reason that reinforcement is there to prevent punching shear. But this only occurs under the ACI design rules for very thick slabs. And so the rules have been changed slightly as to prevent this situation occurring. And what we see on the top figure here on the right is the normal situation with a slab that is, no more than 150 millimeters thick, perhaps. And but for very thick slabs, it happens that we need to extend those top bars as shown in the lower figure. So there's been a new rule added that those bars need to extend out at least 5D, where D is the effective thickness of the slab. It's not H, it's D. D is the distance from the surface to the centroid of the tension reinforcement. So this is a new rule. If you're dealing with a very thick slab and you're concerned about punching shear, make sure that you evaluate the extension of those bars and that they meet the 5D extension rule. Notice one thing that's very important is that extension is from the face of the column, as shown from the center line of the column, but from the face of the column. It's easy for the steel reinforcement supplier to mistakenly provide bars that are where their length is measured or extension is measured from the center of the column. It's from the face of the column that that extension is required. Okay, now post-tensioning. This is post-tensioning is a method that is widely used, particularly in the Western United States, not as much in the Eastern US. And I'm sure that in your career you will encounter it. You may commonly work with it, or it may be less common in the kind of work you do. But there are a few changes there. There is a new requirement for the spacing of non-pre-stressed reinforcement. So this is the normal deformed bars that are in the slab. And that spacing of that reinforcement, which is not the spacing of the post-tensioning tendon, but the spacing of the normal deformed reinforcement, has been reduced. And it is the same now as it is for non-pre-stressed or normally reinforced slabs. So actually things have been simplified a little bit, that spacing is the same. So the maximum spacing of deformed bars in pre-stressed slabs is now the same as for non-pre-stressed slabs. There is a requirement for something we call hairpin bars, as shown on the right, and backup bars. These are needed for post-tension anchorage zones. So what's shown in the bottom two figures is the anchorage or reaction zone for the post-tensioning cable or tendon. And we have found that for when there are several anchors close to each other in plan, spaced out along the edge of the slab, that we need, in some cases, backup bars as shown there with the two black dots in the left figure. And sometimes we need, for thicker slabs, we need what are called anchor bars and hairpin bars. Now, why are we requiring these bars? It's been found that the slab can split under the pressure or the force of the post-tensioning tendons if there's insufficient reinforcement to inhibit this splitting and bursting of the edge of the slab. So these are new rules. If you're involved with this kind of construction, I would recommend that you review the rules for these backup bars, anchor bars, and hairpin bars. Okay, now walls. What I'll be talking about here are not seismic shear walls, but non-seismic walls. And there's a few changes. One of them is that cantilever retaining walls, there's a few illustrations there of loads on cantilevered earth retaining walls, are now moved into the chapter 13, or are designed according to chapter 13. Now, you might wonder, why is this? They're a wall. They were in the wall chapter, chapter 11, and now they have been referred to chapter 13 foundations. What we found is that in 318.14, as shown in the lower part of the slide, that there was some confusion about the reinforcement of retaining walls. Specifically, there were rules about a portion of the reinforcement that had to be on one face of the wall and the portion that had to be on the other. They weren't very clear. They weren't very well understood. The definition of interior face and exterior face was not very clear. And we found that there really was not a strong technical basis for the 1/2, 2/3 rule. So now the rule is that there are 2 layers of bars near each face. It doesn't specify what the proportions are, as long as the calculations work for strength. And there is one exception where that is not required for walls greater than 10 inches thick. So that would be about 250 millimeters thick. And that is for single-story basement walls. Generally, these are found, at least in the US, in residences. So 1 story below ground. Those do not require 2 layers of reinforcement, but all other walls greater than 250 millimeters require 2 layers of reinforcement. Now let's talk about foundations. There are some really significant changes about foundations that I want to go over. As I mentioned, we moved the cantilever retaining wall provisions or design rules into the foundations chapter, and there have been many changes in the sections on the design of deep foundations. So what are deep foundations? Those are piles, drilled piers, drilled shafts, cased shafts, both cast in place and driven piles. They're all the types of foundations that are used in soft soil conditions. And I'll describe why those have changed in a moment. But I also want to note that there have been small changes in the minimum concrete strength required for different types of foundations, and also a change in the concrete cover requirement, meaning the thickness of concrete covering the reinforcement. So first of all, cantilever retaining walls. In 2014, the code described cantilever retaining walls as walls and that they should be designed as walls. In 2019, we had a philosophical change so that these cantilever retaining walls are actually designed according to the rules for a concrete slab. We believe that they perform better, are more economical, and it makes more sense to design them according to the rules for concrete slabs rather than walls. And I won't go into all of the details, but if you look on this chart, you will see that if we design cantilever retaining walls as a slab, as a one-way slab, then the rules for design get much simpler. And in general, that results in a more economical design because it's a little more reinforcement, but it's the same in both the vertical and the horizontal directions. So it's much easier to put into place. It also avoids the mistakes of having in the field, having the wrong reinforcement put vertically versus horizontally. They're the same. And so this chart outlines the differences between 318, 14, and 19. And if you're interested in that, you can refer to the sections shown there. I think you'll find it's an improvement over the last edition of the code. Now, regarding deep foundations, I said that I would explain why there have been changes in all these different types of foundation provisions. The code, the ACI code, mainly addresses deep foundation design for earthquake-resistant structures. In the US, the earthquake-resistant structures are designed according to a seismic design category, that's SDC, seismic design category, with category A being virtually no earthquake considerations for design, and categories D, E, and F being the most severe earthquake conditions for design. ACI 318 addresses deep foundation design for seismic conditions in these higher seismic zones or design categories C, D, E, and F. So it's a subset of the overall requirements for designing deep foundations, but a very important set of conditions. Now, the situation that existed and still exists to some extent in the US is that there are rules for designing deep foundations in the ASCE 7 code, which is mainly a code about loads. There are different and sometimes conflicting rules in the International Building Code, which is the main governing building code in the US. And there are other, sometimes different and sometimes conflicting or inconsistent rules in ACI 318. So what we did was we took all of those rules from those three different major documents and we put them into a funnel here as is illustrated. And we put them all together, we sorted them out, debated them, and came up with one set of rules, which is in 318.19. So you will find a brand new set of revised rules for deep foundations in ACI 318.19. We are still working on getting all of the provisions moved out of ASCE 7 and IBC into ACI 318, but we've made a lot of progress. And the goal is to have the design provisions for earthquake design of high seismic deep foundations all be within one document and be consistent, and that would be ACI 318. So perhaps we'll get there in the 2025 edition. We're going to try. Now, I'm not going to go through in detail what all these changes are, because that would take maybe over an hour just to go through all those changes. So I'm just alerting you that if you're designing deep foundations for seismic conditions using ACI 318, you should go look in the foundations chapter and determine if there have been changes in the ACI 318 rules for that type of deep foundation as you go through your design. So this is not the detail of what these changes are, but it's letting you know that there have been changes. Okay, anchorage to concrete is everyone's favorite subject. When we reorganized the ACI code in 2014, it was a major reorganization. We reorganized all of the chapters except for the chapter on anchorage to concrete, which is chapter 17. And so we decided to leave that alone because there had been some major changes in the previous edition, and we didn't want to go and change it again. But when it came to the 2019 edition, we worked on reorganizing chapter 17 so that it looked similar to other chapters that had been reorganized in 2014. So it looks different. The provisions are generally the same. There haven't been major changes in the anchorage to concrete provisions, but we did add two more types of anchors, which I think are very interesting. One of those is screw anchors. So these are anchors where you drill a dry hole and then install the anchor, which has threads, steel threads, which cut into the concrete. You're probably familiar with these, but this is what is meant by screw anchors. They're very, very useful kind of anchor, fairly easy to install. I like them a lot. They may not work as well in corrosive conditions, but for protected conditions, they're nice. And then we added something on shear lugs. So what are shear lugs? On the left here, first of all, you see a screw anchor, post-installed screw anchor. So a hole is drilled, and that is inserted with an impact driving driver, wrench. And then shear lugs are the steel projections at the beneath base plates that go project into the concrete foundation and provide additional shear capacity beyond the shear V there, beyond what could be provided by the dowel action of the anchor bolts, the four anchor bolts in this case shown in the lower diagram. And in the upper right, you see the one of these shear lug configurations. A lot of testing has been done on shear lugs. We didn't really know what their shear capacity was until fairly recently, at least reliably be able to predict that. So now there are rules in ACI 318 about how to design shear lugs. So we've kind of gained more confidence in how to design and what the shear capacity of column base plates with shear lugs are. Okay, now seismic, a very important topic. I have been involved in seismic design for more than 30 years now, and it never gets old. It's always changing. There's always new things to discover. And in the 318.19 code, we have made some changes in the seismic design provisions. If you would like a complete and very detailed tour of all of these seismic updates, I suggest that you find two articles in Concrete International. They were actually published last year in March and April. S.K. Ghosh and I wrote those together. They cover just about every detailed aspect of the changes to seismic design that occurred in the 2019 code. So I invite you to look at those, but I'm going to point out some of the changes that are most important in this presentation. Perhaps one of the biggest and most important changes is that higher strength reinforcement is now permitted in seismic design. Previously, we had grade 60 reinforcement which is, what is that, 420 megapascal reinforcement, was permitted for ductile seismic design, for flexural elements, and for shear. Now, 550 megapascal and even 690 megapascal reinforcement is permitted under certain conditions in seismic systems. The idea is that we should be able to reduce the congestion, the crowding of reinforcement if we're using higher strength reinforcement. Of course, what's going to happen is that the architect is going to say, oh, you can make all the columns smaller now, right? And the walls thinner because reinforcement isn't as large. So it'll still be crowded. But anyway, this is now available to you, these higher strength reinforcements for different applications. And this table shown on the right, it's a little small, but you could look at it in the code. Table 20.2.2.4a shows what grades of reinforcement can be used in different applications. The table I've shown here is the inch-pound version of the table. Of course, if you look in the metric or the SI version of the ACI 318 code, you'll see these perhaps in more familiar units. But what you see here is everything in green is what's new or what's been changed. And you see that there are a lot of 80 and 100 KSI or 550 and 690 megapascal grades of steel allowed in different applications. So you may find this useful for design in perhaps reducing costs if you're able to reduce the total weight of reinforcement, perhaps reducing congestion of reinforcement or crowding of reinforcement, and perhaps in making elements thinner or smaller. It gives you more options, let's put it that way. Now, as far as when or if these different grades of reinforcement are available from steel mills, that's a very local question. You would need to verify the availability of some of these grades where you're working in your project location. And in fact, in the US, it's not always easy to get some of these grades. For instance, the 690 megapascal grade is a little difficult to find because currently not a lot of that is used. Okay, so those are some new things related to seismic design with higher strength reinforcement. Now let's talk about seismic design of some specific earthquake force resisting systems. A lot of the changes have to do with the availability now of higher strength reinforcement for design. And what I've done is on these next few slides, I've shown where in the green box, where the new availability of steel grades is permitting you to use a different type of bar. So new in 2019 is using grade 80 or 550 megapascal reinforcement, in this case for flexural reinforcements in special moment frame beams. So anything in green on these slides is new in 2019. So I won't go into the detail here, but as you can see, as I go to some of these other illustrations, you see that for instance, the shear reinforcement now can be a higher grade, but also notice that the spacing of the reinforcement is reduced for the shear reinforcement to a smaller spacing, and there's a couple technical reasons for that, but it mainly has to do with the tendency of bars, especially in seismic applications, to buckle laterally between the points of support, which in this case are the shear reinforcement, the hoops in this case, in special moment frame beams. So just be aware, if you're using the higher grade reinforcement in certain applications, sometimes the spacing has changed, decreased slightly. We see here that, again, there's a spacing change if you're using 550 megapascal hoops in intermediate moment frames in this example. If we look then at columns in special moment frames, again, you can use the higher grade reinforcement, but the spacing has changed, has decreased slightly for the higher grade. And then we get to special structural walls. Now, this is probably where the most significant changes have occurred, and I'll try to cover the main points so that you understand what has changed in 2019 with special structural concrete shear walls for seismic. Here is a brief summary of the changes in shear walls, special structural walls, and I'll describe each of these briefly, but in subsequent slides. But the cutoff or the stopping of longitudinal bars, the rules have changed, I think, for the better. Reinforcement ratios at the ends of the walls have been changed somewhat. It probably won't affect in practice too much. It won't affect too many buildings. The shear demand is a very significant change that I'll be spending some time on. That is, the shear load that is required to be resisted by the walls has changed. There's a new drift capacity check, which, again, will probably not influence the design of walls very much. There are very significant changes in the detailing requirements, the hoops and cross ties in the special boundary elements at the ends of special walls. And there is a new section on ductile coupled walls. So I'll go through all of these briefly in the following slides. So previously in 2014, if you had a vertical wall, a vertical bar in a shear wall, and you got to a certain height in the building where you no longer needed that bar because the flexural demands have decreased as you go higher in the building, and you want to stop that bar, you had to, under the old rules, extend that bar 0.8 times the length, the horizontal length of the wall. So if you had, for example, a 10-meter long wall, which is fairly common in the U.S. On the West Coast, if your shear wall was 10 meters wide this way, and you needed to stop a bar, you couldn't stop it where you no longer needed it. You needed to extend it 8 meters beyond that point. So 8 meters is more than, or is about 2 stories typically. So what was required was to extend these bars 2 stories above where they're needed, which in some cases, which is really excessive. And there actually wasn't a really solid technical reason to do that. So we had a lot of debate about that provision. And the new rule is illustrated here. Once you find the point at which a bar is no longer needed, you need to extend it at least 12 feet or a little less than 4 meters, like about 3.8 meters above the point that it's last needed, which is much much easier to build. And however, if that bar, that 3.8 meter extension went above the next floor, then you only need to go L sub D, so one tension development length above the next floor. So it could be actually significantly shorter than 12 feet. So this is a big change from the point 8 times the length of the wall extension that was required. And this took a lot of debate and discussion and voting to get this change through. Okay, moving on to a different topic about walls. There is a new provision, which I have to say is a little bit controversial, regarding the location of lap splices. So lap splices are where 2 bars are joined by overlapping them like this. Lap splices are not permitted now in 318.19 in the zones shown in orange on the right. And those zones are at the base of a wall where a plastic hinge, an inelastic hinge will form. And it's in the special boundary regions. So these are the heavily reinforced regions near the ends of walls or at the intersections of walls, as shown on the left illustration, where there's a T-shaped wall and the boundary regions are shaded in orange. So within those boundary regions, over a distance from the height of the first story above the base, or one development length of those longitudinal bars below, lap splices are not permitted. So unfortunately, lap splices at that location are the simplest thing the simplest way to construct those walls. Obviously, you have short bars coming out of the foundation, and then you continue to build the wall above, and that's the easiest way to do it. The problem has to do with the inelastic stretching of bars in that region. If only 1 or 2 cracks form right at the top of the foundation as the wall flexes back and forth, all of the strain in those bars will end up in the in a very concentrated region, short region, and it could lead to fracture of the bars. So based on research and examination of various studies, the rule was implemented to prohibit lap splices in the orange zones shown here. Now, instead of lap splices, it's possible to use mechanical couplers. And there are, of course, at least 6 or 10 different types of mechanical couplers available on the market. It's recognized that they are more expensive than lap splices. They can be difficult to install, but we felt that it's very important to focus on good ductile inelastic behavior at this particular location in shear walls. So that's the background on that change. Another change, which maybe is a little harder to understand, but it makes sense, is when the longitudinal or the vertical flexural reinforcement in a wall is adequate for flexure, but is not adequate to create many small cracks, horizontal cracks up the wall, height of the wall. Again, that concentrates inelastic strains in just a few locations, which could promote fracture of the bar. This was based on observations from earthquakes in Chile and New Zealand, Christchurch, that only 1 or 2 large cracks formed in some walls, and not very many small secondary cracks. It's just not a good situation, as illustrated by the analysis results shown on the right. So by adding a little more reinforcement in the ends of the walls, we end up with a situation as illustrated here, where there are many small horizontal cracks. The inelastic strain in the vertical or longitudinal bars is distributed well over the height of the wall, and there's less possibility of a strain concentration and a fracture. So immediately you're wondering, well, how much more reinforcement do I need to put in the ends of the walls? There's almost no room in there as it is under the current ACI provisions. Well, this new ratio is 6 times the square root of f times c over fy. I think it's actually different for SI units. This is in inch pounds units. I forgot to mention, in both the SI and inch pound units of the code, there is a table in Appendix C that shows every equation in the code in both inch pound units and SI units. So if you're ever looking at an inch pound equation and you want to know how to calculate it, how to evaluate that expression in SI units, look in Appendix C and you'll find it there. So for instance, there's a different equation for this row for SI units. In any case, this amount of reinforcement needs to be near the ends of the walls. And that results in this much better behavior as illustrated here. Now, let me back up, I'm sorry. You will find, if you're designing walls with this new rule, that in most cases, it doesn't change the amount of reinforcement. If it does change the amount of reinforcement, it's by a small amount. So this is not a big impact. It's just designed to try to improve ductile behavior of walls in a few situations. All right, another really big change is this shear amplification. So just a little bit of background on this, particularly for tall buildings. By that, I mean 15 stories or taller, maybe up to 50 or more stories. In the US, we design those tall buildings, of course, according to the code, but we also generally require in the Western US a review by another engineer called peer review, P-E-E-R, peer review, to evaluate our analysis methods. And I think it's a good system. It provides very consistent levels of design. But when we do that kind of design, now it is pretty much universal practice to perform a nonlinear time history or response history analysis. So we model the structure, this tall structure, we subject it to the accelerations of an actual or recorded earthquake, and we evaluate the response, particularly the inelastic behavior. And we do that for a number of earthquakes, either 7 or 11 different earthquakes for design of the tall building. What we have always found for the past 15 or 20 years is that the shear in the tall walls is always greater than what you would find if you just applied the ACI 318 code provisions for shorter buildings, and that it is necessary to provide more shear reinforcement in those tall walls than would be determined through a sort of a more basic type of analysis. So we have known that the shear demand or the shear loads in tall walls is significantly greater than what the code would tell us for tall buildings. So in this equation, which you see here, V sub U is what you would get from regular linear analysis using code-based provisions. And we find that if you are not going to perform the kind of analysis that I described, the response history or time history nonlinear analysis, that you need to apply these amplification factors to shear only. This isn't for moment, it's just for shear in the walls. And those amplification factors are large omega sub V and small omega sub V. So as I said, V sub U is the shear obtained from the code lateral load analysis with factored load combinations, but assuming a linear structure. Large omega sub V is an increase in shear design force related to the overstrength of the walls. So when a plastic hinge forms, the shear that's generated through formation of that plastic hinge is higher than, and that overstrength factor is greater than 1, and it increases the shear in the wall. The other omega sub v is a small omega sub v. This comes from the dynamic analysis showing that higher frequency modes in the structure for tall structures increase the shear demand in the walls. So these are two known effects that they're now in the code. But the combination of those two factors is less than or equal to 3. So there's a cap. But notice that a building previously designed according to linear analysis, tall building using V sub U may now require design for as much as 3 times V sub U for shear only. This is not for overturning or for moment. So this is somewhat of a shock to us in the design community. It's less of a shock for consultants who have been designing tall buildings for the last 20 years or so using this nonlinear analysis. So we know, because we've accounted for these effects already in our designs for the last 20 years or so, that we have included this effect, but now we're putting this effect into the code to make sure that it's considered in all designs. Here is the way of calculating large omega sub v, so that's the overstrength factor. It has to do with the strength of concrete and what is specified, and that factor can be 1.5, depending on the height of the wall, divided by the length of the wall. And I won't go into the details here, but that factor is 1 or greater, depending on the slenderness of the wall and the applied load hinge moment. And then the small omega sub v is really height dependent, and this n sub s is the number of stories, n sub s. And so we see that for taller buildings, this factor increases. It begins at 1.0 and it increases as high as 1.8. But once again, the multiplying together, the combination does not have to be greater than 3. I want to point out that this equation, again, is in inch-pound units. This n sub s is greater than or equal to 0.007 h sub WCS. That's height of the wall above the critical section that you're designing for, and it is in inches. So you need to use the appropriate equation for SI units if you're evaluating that equation. Okay. This next provision related to walls, it's presented here as a deformation demand check. So a check that your wall can deform adequately and not exhibit bad behavior when it's called upon to bend in an earthquake. What it really is something that affects the wall thickness. It's really a check to make sure that the wall is thick enough that it doesn't buckle out of plane, that is, buckle sideways when it's subjected to high seismic loads that are also cause inelastic action. So in these equations, in equation 2, the lowercase b, that's the thickness of the wall. B is how thick the wall is. And the simple check to make sure that the wall is thick enough to prevent this out of plane failure is shown in equation 2. That's kind of a conservative check, meaning you might be able to get a thinner wall if you follow the second or the third expression, number 3 there. However, as you can see, there are some parameters in that expression for item 3, which you don't know before you complete design of the wall. So to use equation 3, it's iterative process. You have to go around. And we provided equation 2 so that in preliminary design and even in final design, you can just establish what the minimum wall thickness is and not worry about iterating through what the seismic demands vis-a-vis the area of concrete, A sub CV, and so on, that you just use the simpler expression. So for preliminary sizing and even for final design, you can use the minimum wall thickness check shown in item 2. And now there have been some other changes in the detailing requirements for special walls, which are important and, again, controversial. There was not uniform agreement in the committees, the seismic subcommittee and the main committee, on whether these requirements were needed or not. But through the consensus process and through voting and through revision and debate, we developed the detailing provisions, which I'm about to show you. You will see that they increase the difficulty of construction significantly. And that's why these are even now currently in debate within ACI 318. We may issue a clarification of these provisions that I'm about to show you that may make them a little easier to comply with. But I'll show you what they are now as published in ACI 318-19. And if and when there is a clarification of those provisions, that will come out, I'm guessing, within the next probably within the next 6 months, but I can't be certain. We're working on that, though. Okay, so what are these provisions? All of the bars within the special boundary zone, as shown in the gray area, all of the vertical bars have to be enclosed by either a 135-degree seismic hook or a 90-degree bend. So you see in this illustration that every black circle is enclosed or constrained 90-degree corner or a 135-degree hook. This is different from 318.14, where, for instance, the orange bars shown there, the orange-colored bars, were permitted to use a 90-degree hook on one end and a 135-degree hook on the other end. And this was made construction not easy, but possible. Putting 135-degree hooks on both ends of cross ties definitely makes life more difficult for a contractor. I won't comment any further on that, other than to say we are evaluating these requirements now. It's very difficult to build this way. The other requirement is that there be closed hoops that are no longer than 2 times the thickness of the wall, and that when those closed hoops are installed, that they overlap, as shown here. There's a blue closed hoop on the left and a black closed hoop on the right. Again, this is a difficult detail to construct. I suspect that the best way to construct these would be to pre-assemble these reinforcement cages and thread in the bars into their locations. But I'm not a contractor, so I can't predict what the best way to do this is, but it will be a big change. And then the other thing to notice is the orange bars on the right, where it's labeled longitudinal web reinforcement. Those are also required to have 135-degree hooks on each end within the plastic hinge region. So not everywhere in the wall, but in the area where we believe yielding would occur. Again, these are difficult to install. I'm sure there may be some inventive entrepreneur out there who's going to figure out how to do this passenger method of construction, but the test data from laboratory tests indicated that to get sufficient confinement of the concrete at the ends of walls, this needed to be the case. So it's an ongoing topic of discussion, though. Yeah, so I already described this. This is the orange bars on the right. So I've described all the changes there in reinforcement detailing for special structural walls. Okay, moving on to a different topic related to walls is I think we're all familiar with this type of walls shown here on the right, where there are two solid shear walls and they are connected by coupling beams, and that's called a ductile coupled wall. And many thousands, probably hundreds of thousands of these kinds of walls have been constructed around the world. They're very popular in the US. They're a very efficient use of concrete, and they allow openings for corridors and windows and so on, or stairways. But they have never been defined in the code. They're a very common and popular type of shear wall that has never been defined. We all know what official definition. So we now have an official definition of a ductile coupled shear wall. It's given in the code in section 1810.9. And it has to do with the height to length ratio of the wall being greater than 2, and with the provision of coupling beams and what their length to height ratio is as well. Now, you may ask, why is it important that we define what a ductile coupled wall is? It's important because, at least in the US, when we design for seismic loads for each structural system, whether it's a steel moment frame, concrete shear wall, steel plate shear wall, whatever, there's a factor called R. R is to a concrete pile. So